All right. Okay, welcome everyone to a life science session where today we're going to be investigating quite an interesting new programming paradigm as computer programming computational paradigm, which is interaction nets, also otherwise referred to as interaction combinators or interaction calculus, or it involves interaction calculus. But yeah, many interesting topics to explore in this kind of cutting edge computer science direction. So yeah, Nick has worked on this a little bit in Wolfram language, and we've created a couple of notebooks, and it's an exploratory session to see what we can figure out, and hopefully there's some people in the chat that can also contribute and ask questions as we go. So yeah, maybe Nick, do you want to have give it like a brief summary before you share your screen and we look at the actual code of what's the story of interaction nets in your mind? How would you define what makes this interesting and worth exploring?
Well, what was interesting for me personally in this kind of it's just like an alternative computational paradigm, because I was involved in a bunch of not just classical, even in the quantum paradigms, but of course we were looking into all the classical ones from Turing machines, lambda calculus, of course, like stellar automatons and things like that, right? But this is like an alternative approach, which is also related to other things we are interested in, like graph rewriting, hypergraph rewriting. But this is like introduces some other kind of graphs, which are called interaction nets, that are also kind of being rewritten in some form, right? So that particular process constitutes the whole other computational model that you can explore. And it also has some nice promises as being optimal in some way and very nicely parallelizable, and that doing this kind of computation may allow all kind of other crazy stuff happening more efficiently than the other models.
So is it accurate to say this is an alternative to Turing machines? Turing machines is one form of computation which is ubiquitous across the world as kind of the default way that everyone uses their computers, but this is a different way to actually run the computation.
Sure, yes. It's like there's a lot of ways to interpret your computation. Like there's all kind of different paradigms. It's like computation are universal across all different models. That's the whole idea. You can express what actually happens, but at the end of the day, you can compile one computation to another, because all of them are in some sense universal. Turing machine is universal, lambda calculus is universal. This is like another computational model that is universal and can be compiled to both Turing machines and like serial automata and lambda calculus. But besides that, it being like universally universal, right, it has some other properties which are very much promising for the actual practice of a programmer in the future.
Very cool.
At least that's the hope.
And I think two of the big claims here is automatic parallelization. So at least with the implementation that a higher order company and Victor Talon are working on, which is HVM, the idea is that anything that can be parallelized will be parallelized automatically, kind of like behind the scenes. So you just code whatever you want in the high level plain language, and you don't need to explicitly say which is multi-threaded or not. It will just parallelize automatically, which would be a great tool for programmers to use. But there's some other cool optimizations, like inherent optimizations as well. So let's see if we can explore some of that. Should we start at the high level? What are interaction nets, and kind of like just get a grasp of that, and then try to figure out some code?
Yeah, well, yeah. Let's see. We just have some notebooks of just us exploring stuff, right? We can start with just learning those and see how it goes, right? It's like we start with our usual environment. Maybe I'll make it bigger.
Yeah, let's do 150.
Right.
Yeah.
In the Wolfram language, you already have lambda calculus in a way, right? Because we have a function which is essentially like a synonym for the lambda. You can just literally create one and like express all your lambda expressions in the following way. Or you can like come up with all kind of other different ways of expressing those. You can express like combinators, SK combinators like this, so just some specific rules of how those are being applied to other arguments, right? Those are very natural way to express those in the Wolfram language, because it's just underneath is just rewriting and
Is
a
that
bunch of
the
rules.
is that the idea of symbolic computation, or is that like anything can be a symbol at the end of the day? Or
Kind of, in a way, it's like the idea comes from the simple thing, like even if you have like a symbol like X or Y, you evaluate it in any other language, it's gonna complain, right? Because it expects it to be some number. But in this language, like any particular symbol that is not assigned, or there is no rule assigned to it, it's just a symbol on its own, right? And you can carry it around, copy it, like plug it into other stuff. But to any symbol, you can assign some kind of reduction rules on its own that can be then be reduced. Like if you make assign X some number, like 10, underneath what's happening is actually this X. Okay, it's became black, and if you relate it again, some rule is gonna fire and actually reduce it to that number that you assigned it to. But underneath it, what it says that there's like some kind of own values being assigned to this particular symbol X, and this is just a list of rules that tells you that this X corresponds to 10, right? And it happens all like it's through the language everywhere. It's like when you define a function like this, like x plus 1, what it actually does, it takes the symbol f and assigns it, so like in this case, it's going to be down values because it has some definitions, right? So the down values for symbol f is now again a similar rule that tells you what to do with this x, right? So it's just a combination of rules and patterns that make up the whole language, right? And obviously there's anonymous functions like the lambdas that you can do, right? Just an argument and again some body that you can apply, not necessarily using the square brackets, but you apply it to this argument, and that's how lambda functions are being reduced, right? This is essentially a better reduction. It's happening. You can define S combinators, which is again works similarly, just defines down values for the special symbols that we called S, right? We can take a look at the down values. Well, in this case, it's actually trickier because I think it's called sub values now. Well, that's like technical distinction between when you have nested arguments like that. They're technically called sub values, and that's where this rule is being created. But essentially the same thing, right? So we have this paradigm, computational paradigm of patterns and rules being used through the language, but the interaction nets and subsequently the HVM is kind of built on a different kind of abstractions, right? The most basic one is the node, right? Which is, for example, can represent something like a lambda term, right? You can think of this. First of all, the node in the interaction net is something we call like this triangle with a single primary port. Those kind of wires coming out from the node are called ports, and one primary one, and just two or more, but usually just two auxiliary ports, right? So for example, to represent lambda term, you can do it like this. There's some argument, body, and the result. So as soon as there's like lambda term like this, or you can call it like gamma, I think that's usually how it is called, because you can interpret it differently. So it's not really just lambda. That's how I understand it, at least, right? As soon as it gets into contact with another node with the same primary port, so essentially they form this active pair, they call it. This active pair can be reduced. So essentially the same kind of rule being applied to this active pair, so that it essentially annihilates both of those two nodes, and all it's left is just two wires that connect like argument and the value and the body to return value, essentially something like that. Essentially, as soon as you assume there's some kind of substitution of variables happening underneath, it like depends on the actual semantics, what's actually going on, but
it's kind of so it's kind of like a rewriting rule. You have these nodes that are distributed in a kind of like a graph, and then you have these wires that are connected. And where this graph has wires that are connected via two primary ports, that forms an active pair, and then depending on the type of the node, that will determine the rewriting rule to apply. Is that a fair way to describe it?
Yes, in a way, there's like a bunch of rules. In the HVM, there's like an order of 8 rules being applied. Depending on the different types of nodes, there's also like 8 types of nodes that can be formed into active pairs like that. Like there's not just lambda, kind of lambdas being applied to other terms. There's also like some numeric operations happening, like actually adding numbers or multiplying them, or other numerical operations, or some branching operations that essentially correspond to if operators and things like that.
Okay,
right?
But that's like implementation details. In terms of the theory, are there only really two types of interaction nodes, and then there's like a gamma and a beta, I think, or something, or delta. Yeah,
Delta,
so
yes.
the gamma and a delta type of node that has these interactions, but then there's also an erasure and a duplicator node for where the wires, the same amount of open wires that come into the system, come into the interaction, have to be the same amount of open wires at the end as well. So it's kind of like the only interactions are between these two types of nodes, but then there's another two types of nodes to handle kind of like...
Yeah, let's actually maybe should make some explicit examples of a bunch of those rules. I think the interaction calculus itself, I think, contains just 3 rules, like this erasing rule, right? Again, we're kind of expressing it in the Wolfram language notation, like left-hand side, right-hand side. The left-hand side contains a bunch of patterns. In this case, it's just like this node expressions that have some name, like above, right? The name of the primary port, because we want to express them explicitly, and a bunch of auxiliary nodes, which we can create more than 2 in general, but in the HVM, that's going to be just 2 of them usually.
Okay. So is this node, is this a special construction that you create, or was this built into Wolfram language?
Oh, it's not built in. It's like, it's just, I defined my own symbol. It has this formatting that formats nicely as this triangle, right? But on its input form is essentially the same what I typed. It's just, I just instructed the Wolfram language, as soon as you see this particular expression with the head, node, and some name and ports, you should format it as this triangle.
As that.
Right? So that you can, yeah.
It has a visual output.
Yeah, that's what nice is about Wolfram language. It's like, if you work in this notebook environment, you can essentially assign all of your abstract objects whatever formatting you want. So you can make it very visual, right? So that's what make it nice. You just have a visual object, you can copy paste it everywhere, and like if you have some functionality, like maybe it's like there's some makes sense to add them together, and actually you can add an additional rule how those nodes can be added, right? That you can also come up with the definition for that.
So it's good for exploring and researching ideas rapidly, because if you're a visual learner like myself, you just put the pictures together and it'll actually compute.
Yeah, you have to learn how to like make those definitions usually, but yeah, I personally have a lot of experience. Like if you have some abstract objects, you like maybe you're trying to implement some kind of book you're reading about those objects. It makes sense to write them down like this, come up with some nice visual for it, and write just a bunch of functions that takes those values, which is like the usual programming. It's just for example, in the object-oriented languages, you usually define a class and then just instantiate an object and with a bunch of methods how they interact. Here you essentially, instead of thinking in this terms, class and then inheritance, you just define a bunch of rules, right? It's a bit simpler. Maybe it's less powerful for abstraction, but also in the same way, more powerful. You can, if you...
It's less complicated in a way, so yeah.
Kind of I would say like object-oriented programming is complicated in a way. This is like, you can of course create a library of sorts that implements object-oriented programming on top of rules. It's just an addition, but underneath it's like lambda calculus and Turing machine, but you only deal with the rules and symbols instead. Right. Okay. So I wanted to do some actual rule applications that we have in this interaction net formalism. Like maybe starting with this erasing. As long as you have these nodes, right? You can make a list of nodes, right? So if you have a node A with the primary port X, I need to clear those, define them, right? Same B, right? If you have this node, right, and you want to erase it, I actually have a shorthand, I think, for the erasure node, right? So this is essentially creates this node with no auxiliary ports. This list of nodes can be, there's some functionality. For example, you can call this built-in function in the language called subset replace, which just takes a list of symbols, expressions, and some kind of rule like this one that takes, again, another list with some patterns and turns it into some other thing. So essentially, erasing rule takes this epsilon node and some arbitrary other node. You don't even care about its name, right? You only know about it. There's some list of primary auxiliary nodes, and that x in this x, because it's the same symbol, it essentially acts as a constraint that this symbol should be the same. So this x and this x should be the same. So if this symbol is the same, this rule should fire. So if we apply subset replace to this list with this erasing rule, it should fire. Right? What it actually does is just maps over this auxiliary ports this epsilon thing that we use to create the erasing node. And in this way, you essentially you turn this node, right? We just erase the same node and instead attach the new erasing nodes to its auxiliary ports. Right? So that's a very simple definition. That's how it acts. Okay, there's like the next is the annihilation.
So just a quick question on that. So basically, does it rely on the correct labeling of how those wires are going to be wired up?
Yeah, we're going to use like in this implementation, it's just because it's mostly visual. We have to introduce those names of ports explicitly, but in actual efficient implementation, like the HVM is actually doing in Rust and in C, you don't actually name those primary ports, and the way you combine them together is more efficient.
In terms of it's like there's an inherent data structure that inherently defines how these ports are going to be connected up. Like
in a way. Yeah, in a way, there's like sometimes they're explicit, sometimes they're implicit, because you make an actual pair, you already know what the active pair is, and you just store it as one atomic object, right? But if it's not an active, then it's just stored somewhere else, and you know that those correspond to some other nodes, if there is any, right? So essentially, you replace all the ports with nodes. You don't have a data structure for ports explicitly. You only have nodes, and as soon as they connect it, they just literally are part of other node. So essentially, a node is just a pair of nodes, right? You don't have to think about ports explicitly if you want to do it efficiently. Okay, so okay, annihilation. Let's try to annihilate some stuff. Okay, we can start with the same A node, right? I would just make a B and change it auxiliary nodes. Yeah, this one. And apply annihilation. So what? I don't think it applies, right? Oh yeah. So essentially, this annihilation was pretty simple. There's like some variation of that rule that can be done, but here's just a simple one that takes a node with the same name, right, and the same primary port. Now with auxiliary nodes that can be different, right? So in this case, it will fire, not fire because the name is different, but they have to actually have the same name.
So is that kind of like a type? Is that like a node type?
Yeah, in a way, just a substitute for type. You just have a name represent the type of the node, right? So after annihilation, what it's doing here, it has a switch there, even though it's like a single rule. But because I was experimenting with it, there's like, depending on the type, I do connect it with the wire or crisscross them or directly connect the wires, right? Depending on the type, you can do either of those.
Okay, so I have a question here. So if we were to draw out this graph, are we not there yet? Are we just defining, what are we doing here? Are we defining the rewriting rules? Like how things are going to work? We haven't actually created a net yet.
Well, in a way, net is already implicitly defined by the fact that we have a list of nodes.
Okay.
As soon as you have this, you can call it a net.
Okay.
Right?
So how does that net actually look? Like, are you able at this point to visualize those two things actually being connected? Okay.
Yeah. So we have a nice function that does this. Right?
Okay.
Because you take a list of nodes before the fact that they have the same primary port. This function knows that you should connect them. So that's the most simple, almost the most simple interaction net that you can create here.
All right, cool. And
they also highlight red, and I always highlight red all the nodes that have the actual primary ports connected. And
so
I assume they're they're active.
That's an active pair.
Yeah.
Okay, so now I have a question. So there's A, B, C, D, which are the free wires that are kind of like coming into the system. After the annihilation, should there coming out? So should there be again three open open wires at the ends? Sorry, one second.
The wires, they're not directed, right? There's no direction to those wires in this particular model.
I'm on a live stream there.
So those doesn't have to be interpreted as inputs. They can be, any wire can be an output or input, depending, because it's just a single wire. But in the actual program, you usually have, like in the usual program language, you have some initial node or initial network, like main, that's going to have just a single port. It's like a value that it returns, right? So in a way, you usually have a single output port. That just and this, if there's more free ports like here, you assume that they're going to be connected to somehow to the main one, so it's not actually free.
Okay.
Right? Maybe that's not a valid definition, if you call it. If you read the, like in HVM formalism, the network with more than one port is not the definition, right? It doesn't correspond to the definition. Actually, maybe we can go through the paper a little bit.
Okay. Yeah, let's do it.
I think on the British one, I should pull one out.
Wait. Have some YouTube video. Start it randomly. Where was it? So in the HVM paper, they have like the whole definition of what the definition of the definition. Okay. I think they called it.
Can you pop that link to me in the chat just so long? I want to share it afterwards.
No, that's like my internal one.
Okay.
Well, but that's they have it on the GitHub. Let me show.
Yeah, there are some references I put in the description already for people to look at, but I'll share this.
I put it in chat. I'll put it in chat.
There we go. I'll paste it.
Yeah, essentially what I've been calling the definition, they call it a book. So a book is like a name and a network. So it's a named network, right? But the network is defined as something that has a tree and a bunch of redexes, or zero many, right? So it's like zero many redexes that you can apply, and a tree can be a node by itself, and usually it is. It's like if you have like experimenting with a bunch of actual programs. Let me just find main here or there. Like see, if you find the main function in the actual HVM language, is this intermediate representation between the actual language that you should program it, like Bend, and the interaction net. This is like intermediate language, how you compile to the interaction net, how do you wire things together, right? The actual definition has some kind of port or node. You can call it a node, right? And this is like a redex. So this is like correspond to some kind of network that's gonna connect this port that is the actual output corresponding to this book right? How do you actually connect some value to this particular node?
Okay.
Right. But it can be not just a single node. Usually I think it's a node. Like here it's a bit more complicated, but usually it's just one node here in every definition. But it's an arbitrary tree. And then just a bunch of radixes tells you how to connect values to those trees again. That
So-
can be reduced.
So is this what we're looking at here? Is this the compiled HVM code?
Yes, this is the compiled HVM code. It's not handwritten, so it's much harder to read through, but it's still understandable because the language is kind of.
And that's
language-wise
based on interaction calculus. That's based on the what we call interaction
It
calculus.
is based, for example, if you
There. Okay.
look through the syntax for the HVM, you'll see that there's like multiple types of nodes you can define, and because they like this binary one contain two trees, those essentially correspond to those auxiliary ports. So these 4 types of nodes have 2 auxiliary ports that can be arbitrary trees. So they not explicitly name the ports, right? They kind of share. This is like they define this kind of tree structure for their nodes have this tree structure that they just built like this, right? Recursively. Right.
Okay.
But if we are doing it like a little bit more visually appealing, but not very effective in actual in practice. So we're not going to program your computational model to be efficient like this.
Yeah.
You have to, but to understand it, I think it's sufficient.
Okay, cool. So there you have then you have that annihilation, and you end up with basically 2 wires. So you had 4 wires. You had 4 points coming in, and you end up with 4 points going out. But there was some rewriting rule that basically made those 4 points connect in a specific way. And this point, it's like a parallel, disconnected, uncrossed connection. So A to C and B to D. But there are other rewriting rules we can apply, which will maybe have different combinations of those 4 variables.
Yes. Exactly.
So is this like an annihilation rule? Or is this the gamma rule? Is the delta rule?
Yeah, well, you can just this applies to every node, so you can apply to both gammas and deltas. They're treated the same, they're wired together the same, even though in some of the books they're wired differently. But I guess the actual HVM treats them the same. But if you want to crisscross, you just swap the ports, I guess.
Okay.
In a way, you can mimic this crossing without introducing the new rule. New rule how they can link together, I guess. So that's why there's always link like obviously like A to C, B to D, without any swapping. If you want to swap, just swap the actual names. Right, but the node here, the wires, is not like some special type. It's just a node with a single auxiliary port, just for simplicity. Right? That's how I render nodes with a single auxiliary port. Just render it like a wire. Yeah, and the erasure that we've seen above is just actually can be any node with 0 auxiliary ports, right? So in a way, you can distinguish between those 3 different types of nodes, with the different types of auxiliary ports. You just can render them differently, but you don't have to represent them with an additional symbol. Just all nodes don't have to. And this kind of wires, which is again the nodes. That's why it's like I render them a little bit thicker so that you can see that it's not just a wire, but an actual node there. And those kind of nodes, they're not explicitly in the definition of HVM. There's no unary nodes with a single auxiliary port. It's like this kind of single wires are always implicit there when the linking is happening, right? There's like I think there's like there's like a special rule here. I also have it explicitly defined So like as soon as you have a wire, right, which is just a node with a single auxiliary port Y, and the other node, which is like, I don't have it explicitly in the pattern, whether they have the common name, but it's like, but they have this complicated condition that checks whether they have the common name either in the primary or in the auxiliary ports, right? Just checking whether it's the same.
Okay.
Right. Yeah. I also have some hacks around that checks whether it's a free port or not.
Okay.
Because we assume I assume I just when I create those ports manually, I assume that I don't use like door symbols. I don't name my variable like this. But when I create a new one, a new port, I always introduce new ports always have this implicit door in them. So
Okay.
that's why I'm checking whether this symbol name has this door signs. That's just gonna restrict this linking rule to not destroy my nodes when they are free. Like, because like here, if the linking happens, it's just gonna destroy the node, right? And nothing's gonna be left of the network itself.
Okay.
Unless we keep track of what actually linking, of what ports have happened.
Okay. So as an implementation we need to do, there's a specific linking node that's kind of not relevant in the theory, but we have to implement this here to keep it visually stable.
It's actually like acts as, for example, if I have a node, an actual node A with X and B, and this node, which can be written like this, right? If I apply linking rule, it just removes the identity. So it's not about really like in this example, maybe it's not very good. It's not doing anything. It's not gonna do much, right? To this rule, it's not gonna apply because there's not contraction, but not reduction. There's no active pairs, but it usually just removes the identities, right? If you plot this, right, it forms an active pair, but what it actually does is just removes the identity and links this port to this port, so that you're just left with a single node line there. So just the row of this linking rule is just remove the identities.
Okay.
But in the HVM implementation, it's just like somehow done differently. This linking is less local. It's like global. They have some special kind of map of all the links. So as soon as you like any node, any other rule like annihilation happening, and right, because when annihilation happens, you have to create these two identities, right? You create these linking pairs that's like, but there's no node that has a single auxiliary port. You can still link them. Yeah, in a way you can link them immediately, but it's still a regex, I think. It's still in a way active pair. I'm not sure.
What's the regex? What's the definition of regex?
It's an active pair. You can think of it as something that can be reduced or your rule can be applied to.
Okay.
Right.
Okay, so we've got an eraser node, an annihilation node, and a linking node.
The most complicating one is this commutation rule, or maybe sometimes called duplication.
Okay.
So the definition is quite involved, but let's try to make an example. So if you have A, I think this is like, it acts on everything except the deltas.
Okay.
I don't remember the reason, but it's like acted, funny when it applied to deltas and something else. So if you have A, and I see there's like a triple underscore, which means there's actually, it is defined for arbitrary number of auxiliary ports, even 0.
Okay.
So in a way, you can, so if you have a network like this, let's start. Right. So in the same as for the annihilation, like this one. If we take this network and replace it with this commutation rule, set replace, what happens? And if we plot it, because otherwise it's hard to see what happened.
Some duplication
so
has taken place, yeah.
Yeah, so we have now, let's show it as an actual duplication of the second thing, so that we can see that it's delta. So we have duplicated A, right?
Mm-hmm.
So it has B. Well, we can insert more ports, so it can. Well, it's not very nice looking then.
We get the idea though.
Yeah.
But is there an active pair there? Oh, the X is kind of like bending around on itself at the same point. Yeah.
So we can hack it around a little bit, I think, because we can assign vertex coordinates manually.
Okay.
We can assign 1, 0, 0. I think it would work. That's not sure. Not sure. All right, that's better.
There we go. That works.
Right.
Okay.
So if you try to apply your duplication to this thing, you get triple. Well, if you get the same, because you're duplicating it, right? You get 2 A's, but because A had 3 wires, essentially has to create 3 new delta nodes. And because of that, there's a bunch of new ports being created.
But there's still in it. So it's created those duplicates, but there's still another.
Well, yeah, with this automatic layout is not very nice looking, but like this example that we're gonna just run it, I think duplication happens here, right? When it's like this gamma is being duplicated, so it's in a way you create 2 gammas and you just crisscross their connections, their internal connections. So this loop is maintained, but now it's between deltas instead, right? And these connections are maintained, but now they're connected to primary ports. So this become a new active pairs now, right? So that's the here the annihilation happens first. That's the simple rule that we already looked into. Like these 2 deltas are just annihilated together to make this loop. But actually, if you look at this, so in this example, like you can replicate this particular graph on network by this 6 set of nodes, right? Essentially, you start with this weird looking
Good thing. Yeah.
Squid thing, yes. I was looking for the word squid. Yeah, exactly. Right.
So okay, so let's just figure this out. So if we try to understand what was happening, there's 2 active pairs currently. The first active pair here at the top is 2 delta nodes connected, and then the second active pair is a gamma and a delta. So when there are 2 deltas, that applies a certain type of rewriting rule, and then when there's a delta and a gamma, it applies a different type of rewriting rule. The delta gamma active pair creates a duplicate, has like a duplication rewrite, and the delta delta has like an annihilation rewrite. Is that fair to say?
Yeah. Well, that's why in this commutation rule, I've had this exception that one of the node is not allowed to be deltas, so that you don't 2 deltas never come together and duplicate each other indefinitely. Something. Oh, it's not necessarily going to be indefinitely, but in the practice when I tried it did introduce some infinite loops, right? But here, for example, here, like here it's not ambiguous. There's only annihilation rules going to happen, but it's never a duplication, right? They're not going to produce more nodes here. So here it's unambiguously only annihilation rule happens, and here only the commutation rule, duplication happens, right? And just to show it explicitly, we should only apply the annihilation first, and so it's only going to apply to this thing, right? Where it's going to be just reduced to these 2 wires. So it's like another squid-looking thing again, right? But then you explicitly only apply the linking, which removes all of these wires, as we showed before, right? You just rewired all of them. Some port names have changed, so now it becomes like an actual loop in the wires. It corresponds to the second picture over here. So here it's like this arrow has this linking implicit, right? But here we've done it explicitly, so we know that we reduce those wires and rename the ports, right? Now we are ready to fire this duplication, right? We could have done it in a different order, but I'm gonna have a picture that applies every possible orders
Oh,
later.
cool. Okay. So
Right? But
that
it's like
okay. So here it's like arbitrary at the moment. We just the order of applying the rewrite rules are kind of just whatever we want. But yeah, that becomes important later. Yeah.
Yeah, well, it's not important because it's like the underlying guarantee of this model is that order doesn't matter.
It's actually not important. That's the whole point.
Yeah, so you can do it like in parallel and in a different order. Like all of your threads can reduce those active pairs in whatever order they want, right? And if you have a way to dispatch all of those active pairs across multiple GPUs, it's going to be very effective. That's the theory. Yeah, but like in this particular example, we can continue reducing this network. Again, this is like duplication rule happens, reducing this particular active pair, right? It introduces a bunch of, then you annihilate again. Only once, I think it annihilates like this left left set of nodes. So like it becomes two identities over here on the left hand side. Then you use the right hand side, right? Again, two new wires appeared. So we have just, then you annihilate this last delta pair, and all you left is just wires that you just should link together. So, and at the end, you just left with two wires. And that's what we have in this example, right? So all you have is just connected two wires together with these two loops.
Okay, so I've got a couple questions. So is there, specifically if there's two delta nodes, is that different to two gamma nodes? So they both annihilate to form just those wires, but is one version parallel and one version like crisscross? Is that the idea?
Oh, what I've seen, it's like, for example, in the HVM definition, they don't have crisscrossing, I think. But in actual all the books I've seen, they do distinguish.
Interesting. Okay.
In all those references, there is a difference, and that's how I first implemented it. So that if there are two deltas coming, they just connect directly first to the first port. But if deltas gammas connected, they crisscross them. But I guess
two
in practice we don't have. Yeah, but I think it's just it's not very natural difference, so we can get rid of it.
But I mean, isn't that important because that determines which input wires are going to be linked to which other wires at the end of the day? Like if it's A, B, C, D, it's either going to be A and C, B and D, or vice versa.
Well, that depends what meaning you assign to those ports.
Yes, what meaning you assign, yeah.
But I guess you can always decide it on construction so that you never have to crisscross. You can flip around them. Like if you know that it's gonna be like a gamma node and you have to crisscross when it annihilates, you just switch the ports.
Yeah.
So, something I don't know.
I see. Okay, so just the actual execution of the things doesn't really matter. You could have some kind of encoding afterwards that flips the value of the inputs, and then you get the same effective result, something like that.
Yeah, I guess you don't even have to manually do this swapping. It's like by construction, when you create the net, on the construction of the net, you already can decide how to orient your ports.
Oh, I see. At construction, even I see. Okay, that's clever. Yeah, I get it. It's like in the compiler, that could just be a compilation step, basically.
Yeah, I guess. It's like this is like too deep.
Okay.
Into actual implementation details. I don't know.
I get it. Yeah, I mean, there's different levels of which we analyze in this thing. There's kind of like the theory, there's the visualization and like trying to understand what happens. Then there's the implementation layer. So yeah, we're trying to skate over the relevant stuff here to keep it interesting.
Yeah. So the picture here I have already. I think like this shows our usual multi-way system rendering the same example as above, starting with the squid. Right. Oh, I guess that one had a different version, maybe. I think I had one without wires. That's one looking. Because you can remove the wires, this linking can always happen. It's just one step, right? Where's the? Did I remove it? Wait.
Maybe it'll come up.
Oh,
Here. Or was it not rendered? 1 second.
Oh, it's here. Let me run
do you want the
this.
aircon on, babe?
I think it was here, but I removed the output.
Do you want the aircon on? I'll press Windows. Okay.
Do you want food?
While you look for it, I'll be back in 1 second.
Oh, there it is. So here's like this multiway system together with the active pairs without any linking explicitly shown in the graph.
Ooh, there's so many variables.
And you always think there's like every path for this graph from the initial net to the final net is always of the same length. So it has this property, nice property. Maybe that's actually what is called optimal, right? So that in whatever reduction you choose, your actual number of reductions is the same, right? That's kind of in the multiway system language, you just can call that the path length from the initial to the final node is going to be the same no matter which path you chose. So in a way, it's like grid-like.
So wait, let's see if we can understand that point. So sort of by construction, the longest paths are going to be equal. There's some kind of like normal form, or there's some kind of confluence, and every way through the multiway system that ends up at that confluence step has the same number of steps.
Yeah.
Interesting.
Okay. And even further than that, you essentially can, because for each path, right, you chose for the multiway system, you can also construct the dependencies between those active pairs, which we call a causal graph. Like an event, when you reduce your active pair in the language of the Wooper physics, we call it an event. For graph rewriting, we have an updating event that performs the reduction, and when you construct the dependency graph of those events, which is the causal graph, it's going to be the same no matter which path you choose. So I think that's all. That property also holds here.
So this is a visualization of the inherent parallelism, basically. Or is that fair to say? So at the top, if we take the first block over there, you have the head of the squid and the body of the squid, and they can be evaluated simultaneously or in any order. And then is the block going down and the block going to the right, is that dependent on which order you've evaluated those? Yes. Yeah.
This one is the path we chose previously with annihilating the head of the squid first. Right? But you could have like kept the head intact and evaluated the body of the squid. So there's like the commutation rule applied instead, right? And then you again have 3 active pairs. So in a way, all of graph rewriting has this inherent parallelism. But I think that's not the important part. It's like kind of obvious, right? Because there's many places of the graph that can be written at once. But the fact that it's optimal and the fact that right, it's correct and optimal is more important.
Very interesting. So it kind of spreads out. There's a kind of a lot of multiple ways of which you can do the ordering, but then it becomes confluent. It kind of reaches a normal form. And is that the correct use of the word normal form here at the end? The final result is the normal.
Yeah, normal form, you can define it in these terms, I guess. It says the network without active pairs, right? No more reductions can be applied. And
it will always reach that normal form. That's the point of normal form. That's in the definition.
It's not. I think not necessarily, right? There still can be. In a way, I think the correct definition of confluence and even optimality, it's like when I say all the paths of the same length, It's only the paths that can actually terminate.
Yeah.
But there's
okay.
like still maybe there's second path that can lead to some loop.
That's
right,
the whole
but,
tin problem, basically.
Yeah,
So
but if
yeah.
you like mod out this loop and ignore it, and you still reach the normal form, it's gonna be the same or the same length or something like that. Right, but there's still maybe some reduction path that can just be like reducing the same pair over and over again,
Yeah.
like annihilating, duplicating in some kind of weird loop contraction.
So I have a question about that. I mean, this might be too theoretic, but where a path that ends up in an infinite loop exists, will every evaluation always end up at that infinite recursive step? Does it become like non-ergodic? Like if the system is non-ergodic, will it always end up at the step, or will there be certain paths that terminate? Like is that halting problem stepped? Is it like an attractor that will always pull in the computation to that infinite parallelism, or is there a, like, if you take a specific path, you can actually avoid that infinite loop? That's what I'm trying to figure out.
No, I know, like for the lambda calculus, I think I know the answer, right? There's always some kind of optimal, or not the optimal, but the path that you can take that always guarantees to be reduced to the normal form, like something like left outermost reduction path.
That's lazy
Right.
ego evaluation type stuff, right?
But not necessarily, right?
Not
It's just
necessarily.
like a particular way because you have a well-defined choice at every point where your next step is, right?
Okay.
But in this interaction net formulas, I actually don't know. It's like, well, how do you actually guarantee that, whether it's actually guaranteed, right? But I think like in the forum they also mentioned maybe a couple of times that there's some problems with it, or it only arises when you have this detectable property of your program, that it has this weird copying of lambda terms that have duplicating lambda terms that have duplication themselves, something like that. Maybe if you detect this property, then it's kind of have not well defined behavior, right? But when you don't have it, I'm not sure whether they still can have some problems.
Interesting. Okay, so this is cool. So this is the multi-way visualization of this term expression.
Yeah, the interaction net.
The interaction net reduction steps.
Yeah.
Cool.
Yeah, so what else do we have here? More squids. Okay. What is this? I don't even remember. Well, I have more, like a larger example with actual.
Just before we go into combinators, have you implemented the erasure and duplicator node? That was something I was looking at with the visualization page that we saw earlier. There was like a circle node which represented an erasure, and then like a duplicator node which represented, like, in other words, if you have 3 wires coming in and you solve for everything that's possible, you end up with like a duplicator node in the middle. We haven't implemented that in this notebook yet.
I'm not sure what you're talking about.
Okay.
The duplication is it's just what we've been calling commutation. The commutation rule also does the duplication, right? With this introduction of new internal ports between those.
If you want to bring up this very cool illustration visualization that was shared in the HVM community, if you scroll down, there's a section where they talk about the introduction of erasure here. So we actually scroll down a bit more. I think it's a bit further down. Yeah, so you see here, all 3 ports on the left side of a rule must appear exactly once on the right side of the rule. So to achieve that, there's this introduction of an erasure and a duplicator agent. Okay, so I guess that's actually what we were doing. I guess this was introduced in a slightly different way. But the way I saw it is that you have three wires on the left hand side. There has to always end up with three wires on the right hand side. So sometimes you have a duplicator, sometimes you have a razor. But that I just noticed now that is the delta node that we mentioned earlier. So that is basically exactly what we're doing. Okay.
Yeah, I actually went a little bit. I think like a razor node can be sort of like as a duplicator with zero duplication, right? So I kind of think like erasure node on its own is not very special. You have like commutation rule, which is just making this erasure rule as a special case, but your duplicator doesn't have any auxiliary ports.
Okay.
Right.
Cool. Okay, should we look at a combinator expression to see if we can test the understanding here a little bit?
Yeah, let's go through this church numeral first.
Okay.
Because I have like this whole loop. Like the church numerals is like just very simple thing. It's like, right? You can in the Wolfram language you can encode it like this. Like you can create some encoding function that takes an integer, a positive integer, right? And you encode it as a lambda term or function, which is just which two arguments are successor and zero, right? So in order to encode zero, it's just a function that takes a successor and zero and returns zero, so it ignores the successor. But if you encode other number, you recursively encode a number one less than that number, right? What's that called? Oh, it's some. Oh, there's some hacks going on, but that's fine. You essentially encode is just a bunch of lambda terms, right? So that you can exponentiate free. So this is like a church numeral, right? In order to actually turn it into a number, you apply it to successor and zero, right?
Can you quickly define what a church numeral is, just like in like a little bit more in layman's terms?
This is just a lambda term, right?
Oh,
so
okay.
just encoding of an integer as a lambda expression.
I see.
Right?
Okay.
So for example, like here, a church code of zero is just this function.
With
right?
one
Just a
successor.
function. Yeah, you interpret this argument. I name it appropriately so it can corresponds to the successor, but the name doesn't matter. It just takes something and that's something else and it returns the second something, which you interpret as zero. But this argument is encoded as a successor. So if you want to encode,
so it's a way of taking lambda terms and encoding these lambda terms that can represent numbers.
Yeah. I wish like we had some nice formatting of functions. Or we can, in a way, we can do it like, right? If we rename function to like literal name like this. Is it better? How about that? Traditional form. Also,
and what number is that now that you got there?
or like this. So this is just one.
That's one. Okay.
You can kind of squint and see that this is zero here, right? Because it like takes S and takes Z and returns Z.
Got it.
Right? You apply the zero to the successor and apply it to Z, so it's kind of evaluates it. So it actually turns it into, right? And then you apply the successor to it again. Well, it gets it. Yeah, I don't know. The fact that this is like just adds 1 to 0.
Yep.
So let's do it. Yeah, then you can like come up with the lambda term for addition, multiplication, and exponentiation from those representation of integers. So here's like I'm exponentiating 3, taking 3 to the power of 12. So if you expand it, it's going to be like some giant. Let's apply this hack because it looks nice. You get some lambda term like this.
So that's a lambda term. That's a giant lambda term to represent that algebraic operation.
Yep. Taking 3 to the power of 12. But then if you apply this lambda term to your successor function, which is just actually adding 1 to something, right? And 0, then it evaluates to the usual integer because That's how many times you applied 1 to 0 in the end, after you evaluate this whole term or reduce it. So underneath this actual lambda reduction happens, which is implemented in the Wolfram language, right? Which is not maybe not very optimal, and that's what like HPC company tries to mitigate, right? And actually, so in a way, we're hoping that our Wolfram language emulator in the end can be written using something like this interaction net formalism, so that it can be naturally parallelized across spreads, so that this kind of lambda term reductions, if you write programs like this or similar to these programs naturally in the language, in this functional style, they can be reduced more efficiently than it currently is.
So is that 531,441, is that the result of the algebraic expression, or is that some, yeah?
So that's the result of this.
Oh, it's a, yeah,
right?
it's an exponent.
But instead of doing that, it's like expands a giant lambda term when you're just adding 1 at the end. That's how many times to 0 to get this number.
Just a random question. So is there like a church numeral encoding for SK combinators? Is it even a valid question? Like how far away is SK combinators to like lambda expression, or is it like even way more primitive?
I was reading this book, and they had something, which is this optimal implementation of functional programming languages, right? Just like a book from 19, and they had, well, I read it for a different reason, right? But they had this in the beginning, I think, somewhere, this implementation of SK combinators using lambda calculus, or other way around, I guess.
Interesting.
Right. So, for example, like this identity lambda using SKK. Then, if you want this, there's some condition that the variables is not in the body, but yeah, I think you can do it.
Okay. Interesting.
That's how you compile lambda terms to SK.
But that would be I'm assuming that'll be a much longer expression. Like to actually write out that SK combinator will be like quite a massive thing compared to the lambda term.
No, I don't think so. I think it should be relevantly of the same size.
Okay. Interesting. And I think that's also something interesting to think about with regards to interaction net. It's kind of like a graphical implementation. Is that the right way to think about it? Like the encoding is in the form of a graph. So it's like almost visual first. And then you can decide how you want to translate the graph into calculus, I guess. And I mean, that's the point of interaction calculus, is that how do you convert the meaning of these graphs, connecting and nodes touching, all that kind of stuff, into something you can write out almost like textually. Is that the right way to describe it? Yeah.
I wouldn't think of it as some kind of graphical language that you should think directly in terms of graphs, right? Usually those graphs is just a representation one can use to effectively reduce your language that you've written using conventional functions and applications. Right? I don't think you have to think directly in terms of graphs. Like maybe Victor knows how to do it at this point, to think in terms of graphs directly and write your algorithms using those. But for the lay person, I think it's not yet the right way of doing it. And I don't think that they should think so in terms of graphs.
Okay. Makes sense.
Yeah.
Maybe it depends on how you think. Yeah. Some people are inherently visual. Graphs makes more sense to me, that's for sure. But yeah, figuring out how to position stuff is difficult. Okay, so let's go back to this church numerals thing. So are you saying that there's a way we can evaluate this expression in using interaction net?
Yeah. So, well, the way it's not directly from the Wolfram language. Maybe at some point we will make some converter. But I have this essentially the same encoding of church numerals encoded in band, right? So you still have like this encoding. You code F and X, but this is the success and 0 again, right? But essentially the same kind of thing written in band directly.
Okay.
So encode the integer, only did multiplication, for example, and kind of comment out all the rest. And for example, we want to compute something simple as multiplying 3 by 2.
Okay.
All right. So you can take this band function program, compile it to HVM. This is
Mhm.
like this language that directly specifies how the interaction nets are knitted together.
So you've created a parser for this though, right?
Yeah. Like took some time. It's like this is like the actual parser. It just takes some. I use functional parsers from Anton Antonov. It's like a very cool guy who makes a bunch of like grammar related functionalities for the Wolfram community.
Okay.
But so he has this simple implementation of functional parsers that's like very easy to use to define this kind of parsers. So just defined all those primitive parsers that involved in the HVM, like create some bunch of nodes. So at the end, all we do is like also there's also evaluator, but just to see what happens when you parse a string like that to a file, essentially returns an association like this, right? So every definition, like this definition decode here, main on encode and also multiplication, like this multiplication is just got parsed into this tree expression. Well, at first it's just expression, but because all the expression in the Wolfram language is just a tree, it essentially parses to this kind of representation, right? So it's like some hierarchical thing. It's like we have defined a net, and a net is just as we seen in the paper, right? The net they define as a tree and a list of redexes, right? So that's the tree, and the list is empty. So multiplication by itself doesn't have anything, but this network, the main, actually does have a bunch of redexes. So its tree itself is just a single node, the output node that outputs the result of this program. And this is like 4 redexes that define, like this true, I think you can ignore. I think it's just some internal thing that defines whether you parallelize. I don't know actually what it does. I forgot. Like there's some kind of special flag that each of the redexes have.
Okay.
Depending on the actual HVM implementation takes into account. But the redex is just it's just a pair of nodes, right? If you look at the paper, redex is just a pair of trees. Again, so just this thing. So this is one tree, this is another tree, and the fact that it's like connects, it just essentially defines how those primary ports are connected to each other. So this defines one node, this defines another node, and the fact that they're like were part of the redex, it tells you that they are connected by the primary port. So in this representation, all of your primary ports are implicit. You don't actually create the name for them or whatever. You just your redex defines that you have two nodes and they form an active pair. That's it, right? And the actual node only stores the pair of the auxiliary other nodes. So yeah, no explicit storage of the primary ports in this formalization. But what you can do, right? After you have this tree, you can just HVM thing. You can turn all these definitions into a list of nodes, introducing a bunch of names, some random names for those ports.
So kind of like UUIDs, something like that.
Yeah. So because all the primary ports are completely implicit in this formalization, I always have the name starting with X, right? But the auxiliary ports actually have the names, right? And that's why I called it VA. So this A corresponds to the actual A in the language. For example, let's take, for example, multiplication here as like VB, VC, right? Those correspond to the actual implicit names. So this A, B, and C's, they actually have them here. So those correspond to letters. Right.
So just to check our understanding, what expression are we evaluating for this one? What's the is it 3 times 2?
Yes, this one.
Okay.
So like this is the whole code. You can actually run it right? So if you run HVM, run this thing, right? It puts 6, so 3 times 2, right? So and there's like 126 interaction happens during this evaluation.
Okay, so you have 126 interactions, the result, which results in the number 6, and that ran in quite quickly. And
Yeah, it's immediate because it's pretty simple. Because we want to actually look at the graphs, right? So it's like after we parsed it, and like introduced all this explicit ports, kind of, and we can turn them into actual graphs and nets connecting those ports together.
So there's
right? And
so the fact that the graph kind of starts off relatively small and kind of expands out is because there's some duplication nodes involved that are required to figure out how to eventually get this thing into a confluent result. So there's like potentially an expansion process before it simplifies down into a end result.
Yeah. Right. So yeah, so the evaluation starts with this main node, which has 4 active pairs already from the start. So it essentially corresponds to 4 different definitions involved in our definition of main. So if we in the band we defined main using decode, multiplication, and encode. Right? What is the other one? Yeah, we used encode twice, right? So to encode 3 and 2, we multiplied them and then decoded it back. So that's those nodes correspond to those particular operations, and they use this special type of nodes, which is lazy. It's the only thing which is lazy in this implementation, right? It's how those references to other definitions are expanded. So when you reduce this pair that uses the definition, right, it just looks into this table of nodes. It looks like, for example, if you this pair is reduced, it looks up the definition for decode and replaces it with this definition, right? It connects the primary ports, right? This is the single port output is here, right? So it connects here this port to whatever port was here, right?
So and why is that not fleshed out initially? Is that because there might be some kind of annihilation that doesn't necessarily need to even think about it? Potentially, there's certain situations where you can even forget about the decoding step. That's why it's not inserted into the initial program. Like, in other words, why
it's not in line? What do you mean? It's like using a reference and not like imposed in this definition of decode in line?
Yeah. Why is it not just automatically stuck in there?
Well, I think it's an optimization. I think it's like pretty sure they maybe have some kind of directive to, like in other languages, I know you can like write some kind of programmer. You can say, okay, this one is in line. Then like every use of decode in other definitions is instructing it to be expanded. So it's actually like not lazy, but eagerly put it in place. But in this in this case, you're not gonna have a benefit of reduction. Like if you specify that encode should be in line, right? And you use it in code twice here. Essentially, when it's gonna be expanded directly, you get kind of duplication of nodes, right? But hold on. I don't know what kind of bad behavior or some non-optimal results can happen from this.
I mean, it's kind of like the same way that you want to lazy evaluate in like Haskell takes lazy evaluation as the default. It's because in certain situations or in most situations it's optimal. It's a better. It leads to situations that actually end up with results instead of infinite loops. So it's something like okay. Cool.
There's definitely it's like this is like what programmer has to be intuitively be able to do this kind of thing. What kind of definitions has to be defined in line or not. This is just like optimization part of the programming.
Yeah, so now we're touching on some implementation implementation layer here basically.
Yeah.
Okay, cool. So you've taken the compiled HVM form and you have a parser in this notebook that converts it to this graphical representation, which is pretty cool.
Yeah,
Very nice. And then does it evaluate as well?
it does. It does.
Mm.
So let's show. First of all, I have like in the process of making those diagrams a little bit better, but in more general framework of specifying this interaction nets.
Okay.
So maybe those nets automatically doesn't lay out nicer, but in the end, we want to improve them. Where is it? I want to improve, like I'm working on how to define these nodes more generally, not just for interaction nets and HVM purposes, but like even for the quantum circuits. But it's like for the future. But in the end, hopefully we're gonna make like a general framework or specifying nodes and what the algebra of those nodes and how they make up diagrams and circuits for all kind of different applications.
Very cool.
But right now, we have like what's different from the just basic interaction net rules. HVM has an additional ones. So we think this is like a narration. This is linking. This is the expansion of the reference, right? It uses some kind of lookup table to the definition of nets. I think it has to unify the names because they can use the same name for the essentially ports. Like if you look at the table, at the HVM version, like this A should not be linked to this A, all right? So kind of definitions has to take it into account that this A actually unique to the definition, right? That's why you have to unify all the variables.
Sure, yeah.
Right. Yeah, and then do some substitution of the primary port. I think that's what happens here. Right? There's some switch operator, switch rule, just kind of when it being reduced with the numerical node, it knows what to do depending whether it's 0 or not 0.
Okay.
Right? There's some this is somewhat of an exception rule because it's not actually in the way I defined it using the subset rewriting. It takes, instead of 2 nodes, it takes 3 nodes.
Okay.
Right? So but in the HVM code, I've seen that they actually do it like some kind of deep lookup. It's still 2 nodes like this that have the primary node touching each other, right? But it's like when this active pair is reduced, it looks into this particular auxiliary port, into its definition, and see whether it's an actual operational there. And depending whether it's operation or not, it does different things.
Okay.
Right. But here I just defined a new rule that takes these 3 pairs that already know that this is connected to this auxiliary port. Right. So because you can do it. So and then you just define. I was lazy. I only defined it for addition. Right. So I only have like the addition rule. So it's like if this operation over here is addition, and then you just add this m to this m and make a new node. Right. But you can essentially define all the numerical operations that HVM can work with. Right. Okay, this is the annihilation thing, and this is the commutation. So there are just few rules, like 3 rules, I think, are required
to actually evaluate.
Yeah, to make an HVM out of interaction net.
Wow. Okay, very cool.
So you need to support different references, branching, and numerical operations. Okay. So and we start with this main node, and just in order to evaluate in this very slow evaluator of HVM programs, you just apply these rules to the main net indefinitely until there is no further reductions can be done. So you run it to the fixed point, right? So you get like a list of evaluations. So if you plot all of those, right, you get essentially this list. Let me make a column. Something, I don't know. Yeah, it just goes through. It's like starting with main, reducing. So
is this still just 3 times 2?
Yeah.
Okay.
Well, it's a lot because like even when we run HVM directly,
126 interactions.
So in a way, it's like it should be. Maybe there's some differences, but it's around 100. red pairs in total.
And then each time you do the reduction, yeah, sometimes they're reducing multiple at the same time for each next reduction.
Yeah, it's multiple, so it reduces all 4 here to get to this one.
That's like in
Then
parallel, basically.
Yeah, in a way, yes.
1,
So
2,
all
3,
4
4.
reduced to get.
1,
This
2,
is
3.
the new 4 pairs. This is essentially just expands all of these definitions. Right? So this is like the other definitions that appeared in the decode. This is like some subroutine of the encode and all that. Right? There's no multiplication and decode encode explicitly there. Yeah. And at the end, what you get is just the answer.
Number 6.
So you get the numerical. The last operation that happened is just in adding 1 by, I'm showing, I'm writing only the active pair, but it actually applies this exceptional rule that takes 3 nodes at once and it just adds 1 to this 5 to get.
Since it's an encoding, if you change the numbers, if it was
that's
like
how relation works.
There's a bit of delay there. Can you hear me now?
Yeah.
If you were to change the numbers and just say like 5 times 2, would it be the same amount of interactions if the numbers were just different? Or would it be a completely different evaluation?
Yeah, because it's a church numerals. Depending on how large is the number, the more interactions it's going to be. Because it just adds 1 at the end, right?
Yeah.
That's how we encoded it to see how does it.
Yeah, so actually the larger the number, the more interactions, basically.
Yeah. Can try. So I have this nice, we can run bend directly, right? So if we change this 2 to 5, right, and run it, now it's like 200 interaction.
1 times 1?
Yeah, it's gonna be not much.
Should be 2, right? Oh, okay.
No, it's like you still have to reduce all the definitions. Like if it's 0, then it should be minimal. 23.
23 interactions.
Actually, let's take this example, see what happens with the graphs. Let me relate this thing. So now this one, we could have changed this 0 directly there. But now, like the structure, it's not changed at all. They only changed the 0 here. So the main node is, the main node and all the definitions are exactly the same. But when you evaluate this to the fixed point, it's going to be much smaller. But let's just see what happens. So first of all, you expand all the definitions. And because they're recursive, this kind of some applications happening there. There's some linking is going on. You can count. Let's count. It's 4, 8, 13, 16, 20, 25. It's much larger, seems like.
Some additional optimization, probably something happening in HVM.
I don't know, because I'm also counting links. Maybe
okay.
Linking rules are not counted. So it's like this 4 counts, this 4 counts. But here it's only linking happening because it's like some wire. Maybe it's not counted. But here just those 3. Maybe 11. It's 13. Just 1. 15. It's no.
So I've got a question. Why are those separated out? Why are these kind of like disconnected there at the bottom, those 2 reference?
Well, some of them are actually garbage collected at the end. So like atomic garbage collection, what you're getting, they can be disconnected, yes. But that's the point, that when they're going to be, then the reduction essentially equivalent to garbage collecting. they're just gonna disappear. I don't care about them.
But if it's duplicating here, isn't it going to first expand? Isn't it going to like suck up a few interactions before it actually gets
Maybe.
deleted? Yeah, interesting.
Perhaps maybe that's like one of the, because it's like it still counts as an active pair. Maybe this is one of the optimizations one can do. So you don't have to actually do anything to it, just throw away this redex altogether. Right? Maybe that's what happens, because I count a little bit more than 23. So maybe they just, those don't count.
How did they get separated? Actually, that's an interesting question. So scroll up at what reduction caused them to separate out?
Well, let's see. So I think this guy. So when those, see this delta over here, right? When these two gammas annihilate, right? This delta I think gonna connect to this reference here.
I see, and that splits off then. Interesting.
Yeah.
So it's almost like when two erasures touch, it should annihilate into nothingness. Something like that.
Well, that's already is the case, I guess. Right? Because erasure, if there's no auxiliary parts, I don't think the erasures ever touch each other. I don't know.
But they. Oh, I see. Okay, yeah. Oh, okay.
But if they do, they just should annihilate.
Very cool. All right, so I saw at one stage you had this way to actually visualize the interaction, kind of like on a little visualizer that you run it, and then it shows all of the interactions, kind of like crunching away.
Oh yeah, I got it. I had this. No, it's not very pretty, but you can. Where they have the graph? Oh yeah, here. Right. If you essentially just the same interaction nets, but without rendering of nodes, just as graphs.
Very cool.
That's how this reduction is going on. Is happening. This 3x2 example.
And that last solid node is the 6. Yeah.
Yes, exactly. Yep, that's just the 6 there.
So all programs that reach confidence will end up with that one solid node.
Well, it's not necessarily going to be just one solid. It's just for this example. But when your final tree is not just a numerical node, it can be any tree. So it doesn't have to be a single vertex at the end.
Sure. Because of the encoding. So yeah, I get it. So
like those lambda terms we were reducing at the beginning, those are very large trees, right? Not just a single numerical node.
So how do you know when to stop? Because there's no reduction that can take place.
Yeah. There's no red. Right? As soon as there's no red at the end, you essentially reach the normal form.
Oh, I see. So if you go to that second last step, that there's only one red in the second last step, and then then there's 2, and then there's 1. Okay.
So this is one. This is that add +1 operation. It actually acts on all of those.
That's that when it looks into the A and determines that it's an addition. Yeah.
Yeah. It's not here anymore. But yeah, I think that's it.
Very cool. Any questions in chat for that cool exploration? I do have one question. So I know we've chatted about this a little bit before, but I'm still fascinated by this concept of croissants. Maybe it's just because they're my favorite French patisserie snack. So it's visualized in my head, but there's in the theories there's this concept of bracketing croissants. Do you have a way of roughly giving me a sense of what those are for?
Well, it's trying to understand it like today, sure, right? But that's why my motivation to start reading this book.
Oh, okay.
Because they introduced it like somewhere in the first 50 pages, and that's the only that's where I get this. Where's the definition?
There's a connection to
yeah.
fans apparently. Like,
Yeah, this is the croissant. Right?
okay.
But like the high level reason this kind of object appears, because this is in the context of just optimal lambda term reduction, right? It's not interaction nets per se, right? But you can still think of lambda terms forming all this kind of trees and graphs, and you can introduce this essentially delta nodes, right? So that you can have this duplication explicitly. But the point of introducing this interaction is because you're gonna have ambiguity, because there's some kind of still graph reduction is going on. In order to reduce the lambda term, you have to apply a bunch of reduction rules, the following one, right? This is what kind of the same kind of rules. This is the duplication rule. This is the annihilation rule. You interpret those as lambda being applied to some argument of the lambda term. This is the annihilation rule. But you can see that I think these rules that combine these two fan in and fan out nodes, as they call it, right? There's actually some ambiguity of whether this rule applies or this applies.
Okay.
Like in the physics terms, in the Wolfram physics terms, we would call it as some kind of quantum effect and branching happening because we have an ambiguity of what the actual rule applies. And depending on which branch. Yeah, so it's kind of, you can essentially spawns or forks multiple branches that are completely independent of each other. And one of them is going to be correct and another one is not.
What is how do you explain that in the physics project context? How are you explaining those ambiguities, or what's the term to describe that? Because it's not like a multi-way chain, because a multi-way chain is like if they become causally invariant, it's just a multi-way computation. But that's different, like causal invariance is different to a multi-way path. Like what you're saying here is there's ambiguity of which rule applies. That's different to a single rule having ambiguity as to where it's applied. Or is that considered the same thing?
Well, when I say ambiguity, I usually like in the terms of Wolfram language rewriting. There's like multiple ways you can create ambiguity with arbitrary rewriting rule. Right? It depends on what objects you're doing it. Like, for example, even for the integer, I can apply something like, okay, if it can follow two alternatives, right? Or maybe I just apply like, I literally have two different rules. It either can do +1, or it can multiply by 2, right? If I have these rules, both of them can be applied simultaneously. So there's no particular way to distinguish them. In this case, it's just gonna apply the first one, right? Well, maybe let's apply it to 3. So it's obvious. It's added 1, right? But if I want to apply all of them, like to see all the possible alternatives, then it's going to be like two different results, right? So that's essentially resolving this ambiguity. There's no natural way of resolving it. You just apply all possible ways.
Okay, so this is an ambiguity in terms of how to, or which rule to use. But there's also ambiguity as to when to apply a well-defined rule in which order. There's like a dependency that gets created.
That's like a time operation. Right?
Okay.
You can, of course, you can, if there's like an expression, like if I had this f, 3 and 4, right, and instead of replace list, I was acting on, can I change the level? Essentially, if I could have applied this set of rules either to this sub expression.
So there's two forms of ambiguity here now.
Yeah. But here it's like not important because that you obviously like space-like separated, right? You can apply these rules in either 3 or 4 in any order to get the same result. But the fact that you have multiple rules, or maybe you have some ambiguity in the pattern, you can create some ambiguity in the pattern, or maybe in the number of outcomes. Maybe you like explicitly say that your right-hand side returns multiple results. But making some sort of superposition, right? That's like what kind of in the HVM they have this term. You have this term representing a superposition of two terms, right? And in a way, in order to create one, you can also say that my right-hand side of my rule creates the superposition explicitly, right? But it's kind of, you could think of it as ambiguity, in some sense. But the point is that there is ambiguity and you can apply it. And like here, it actually was, in the book, it was this ambiguity, right? It's just actually two different rules. You either annihilate or duplicate when this fan in and fan out combine, right? And I think that in the lambda reduction world, like it's very important to distinguish between them. It's like it's not like when you try to reduce some complicated lambda term like this, when there's fan ins and fan out, when they have this enclosures pictures. No, it was before the actual croissants. Essentially, you have to distinguish when the somehow keep track of those fan ins and fan outs in order to know which one of those rules apply, in order to actually get the correct result.
Okay, so you know, is one a bracket and one a croissant? Like if there's a duplication, is that one type of thing, and then
no.
Fan interactions.
Is like, yeah. First of all, there's a problem, like this problem of ambiguity of these two rules.
Got it. Yeah.
Right? There's a problem, right? And brackets and croissant is just a particular solution to that problem.
Okay.
And the problem is, and the particular solution is to essentially keep track of that fan ins and fan out. Oh, here, this is the example. It's like those. Essentially, if you look at this locally, they should be reduced, right? But for some reason, it's not incorrect to reduce them, right? Because it's like some of the fan ins and fan outs are not actually corresponding to each other if you interpret them correctly. So in a way, there's some ambiguity. Just having this reduction rules on its own is not enough. You somehow have to keep track whether it's allowed or not to actually reduce this pair. Why do you annihilate or duplicate it?
In order to avoid the ambiguity.
It's not just ambiguity. So literally, if you do the wrong thing, you get the incorrect result.
Interesting. Okay.
Right. So this is and when you say how to resolve this problem, then you start thinking about other solutions, and croissants and brackets is just one particular solution, how you keep track of those things. Right? You just it's like involves these levels. Right? Essentially, when you contract those things, you also keep track of the levels. You also assign this level to each of those croissants, and each of those brackets, you assign some sort of level, and when they come together and they're of the same level, then they can be reduced to a single wire.
Okay.
Right. And there's also a rule how any node can pass through those brackets, and there's a solution, and there's like a constraint that the level of the node has to be larger than the level of the bracket.
Okay.
Right. Then it's allowed to pass through them, and this somehow, I don't understand why, right? Because I only read this. I only read it like very on the surface of it, so only the high picture.
So it's kind of, it's not that elegant. It's a solution, but it's not necessarily that elegant, and it kind of creates this sort of additional complexity overhead potentially. But
yeah, maybe that's exactly the same kind of overhead like Victor refers to when he said that if you want to support full lambda calculus, right, you have to reproduce some kind of overhead with something like this croissants and brackets, or maybe something else, right? But in order to support lambda calculus completely, you somehow have to introduce this kind of overhead.
Now the whole narrative is starting to come together, and kind of the decision that they took was to not support full lambda calculus, and rather to support a subset of valid lambda expressions, which is enough, which apparently is enough to be Turing complete. Is that a statement?
Yeah, I think so. It's enough to be Turing complete, but there's some natural operations that are forbidden by default. For example, like this exponentiation of Church numerals that I have here, right? I think that one is not allowed in HVM when it doesn't reproduce this overhead, right? Because it's, I think actually if you try it, let's try it. We had this power, which is the exponent. If you want to compute 2 to the power of 2, right? If you run it,
Uh-oh.
I think it's just out of memory here, right? So it's broke. So then it depends what kind of I don't know what kind of optimizations are involved in order to mitigate this problem.
Mm-hmm.
It's like as soon as you detect that you have this higher nested lambda terms that are duplicated, that themselves contain some duplications, if you detect this kind of situation, you can mitigate it. So you only have to introduce this. Either you just give up and give an error, or you do introduce some kind of croissants and brackets in a more efficient way. But only when this situation happens that you have to fall back in order to be correct.
Duplicating duplicators are not good.
Yeah, but most of the time the claim is that you don't have to have this kind of situations when like this Church numeral exponentiation, and all the algorithms in the computer science can be implemented without those, so that you don't have to keep track of those croissants and bracket. So and that's gonna give you like 10 speed up.
Okay, so croissant and brackets is part of the story of the theory, but in terms of the implementation that HVM has taken, it's not relevant. They're not using brackets and croissants.
Yeah, well, only when they,
unless necessary.
This fallback, yeah.
Okay,
because if they want
yeah.
an actual usable language, it's not gonna like they're gonna okay, you wrote a program that we can't deal with.
Yeah, of course, yeah.
Go away, right? They have to, right? They actually have to do it in order for it to be usable.
I think another interesting thing, and maybe we can do a part 2 on this because the stream's getting a bit long, but what's interesting with Bend is that they have these ideas of folds and bends, where in order to traverse, like instead of loops, you have these folds, and then folds unfold tree-like data structures, which are bends. And that's the way which you do iterators, I guess, is in a specific kind of way. Is that kind of like one of the constructions that are implemented in order to make the thing usable?
Well, I wouldn't say so. It's like if you're already familiar with the functional programming language, like Haskell, which is very purely functional, right? You already know about fold. It's like every kind of loop there is can be formulated as a fold there, right? So you don't ever write like for loops and while loops. Usually write some kind of either using some tail recursion or some kind of folding operator. And what they call bend is just the unfold, as I understand it. Okay. It's just the reverse of the fold operation when you start with the initial condition, right, and try to make the data structure by nesting some operation over it.
So can you only fold bends, or can you fold any?
No, that's like no.
Okay.
No, I don't think so. Well, I'm not familiar too much with the actual bend, how they use the bend. But if I think about fold and unfold, like maybe I have Haskell here. I don't remember. Yes, I have Haskell installed, so I think you can. The type of fold, L. It takes some kind of function. I don't know whether you can read it, but this is like a type of the fold. Yeah, it's like this is the type of the function that takes argument of type B and argument of type A, returns an argument of type B. Some initial value. Why is it? It's some kind of container, like a list, and then returns a B. So it's like this represents a container. So it's essentially folding a function with some, maybe there's like fold one, so initial value can be ignored. So it's folding over a list or a tree or any data structure. It's folding over your function and returns some other value, right? But there's also unfold, I think. Really? Maybe maybe called differently. Maybe it's some kind of library. I haven't coded in Haskell for a long time. Maybe it's some kind of library.
To unfold. Okay.
Yeah, I think it's maybe like import data list. Oh yeah, okay. So there's there's an unfold, right? It takes again some kind of initial value, but then the point is that it returns some kind of container, like a list in this case, right? And the function, it kind of has this branching, some kind of way to branch, whether it's so that you can specify whether it's a base case, so you can stop your recursion, so you can actually stop making your data structure. That's why it's a maybe. So I think that's essentially what went is, because you can specify this when, right? Here, essentially your base case is like maybe just it's a way to continue your recursion, or when depending on whether the function returns nothing, you can stop the recursion and return the data structure. That's why bent is like fold.
Okay. Okay, so and then I guess you could put so the bend is in that. All right. But then I remember something about a fold having branches and leaves and that sort of thing. But that, I mean, again, that's just like a tree structure with the leaf being a stopping point, I guess.
I wonder whether Wolfram language has an unfold. I don't think so. What's the natural way to call unfold in Wolfram language? Because we have a nest, just nest maybe. You just fold fixed point, threefold. So we have kind of functions that this is fold function, then right? That they take some kind of take a tree, some kind of functions, return an expression, arbitrary expression, right? It may be an integer, but the reverse of that. I know what kind of function can be thought of this. It's by our friend Brad. It's essentially like takes a graph and a function. It's a bit design is a bit weird, but it's like taking a no, it's still a fold. No, it's like it's a
Starting to fold my brain now. I think we're starting to reach the end of my ability to keep track of what's going on.
Yeah, the most closest thing is like the things that are prefixed with nest, because they always start with some initial condition, maybe nest graph, right? In order to make a graph, you start with a function and an initial condition and apply it some fixed amount of times. But instead of how many times you want to apply it, you have a way with the function to specify when to stop. So that's the difference. Maybe we need this kind of abstraction. It's kind of shame that we don't have it naturally. Maybe
interesting.
Nest while. Maybe nest while is kind of because it has a test.
Okay. Yeah.
Okay, so instead of how many times you have a testing function. Maybe that's fine. That's it. It's like nest while family functions. They apply some function to some initial thing and can build some data structure or value, and you have a condition to stop. Yeah, it's fine.
You can iterate through that basically.
Yeah. So bent is like nest while.
Okay. Okay. Very cool. Yeah, that was awesome. It's very interesting stuff. There's a couple of examples that I would like to work through where we can actually demonstrate the power of this methodology and this paradigm. Probably maybe not on this stream, but maybe the future stream we can. There's some tests we've been playing around with where we actually take I think using like an SK combinator or some type of church numeral encoding, running it in Wolfram language to see what the the Turing paradigm gets you in as optimized way as possible, and then seeing if interaction calculus and interaction combinators could make it a ton faster. Do you have an example at hand, or is that something we should probably work towards? Figure out if we can have a good example.
Which example are you thinking about?
There's that SK combinator that has something like 140 million steps before it reaches normal form.
I think that would. Where that one? Like this one?
Yeah, that looks like it. This is interesting because basically evaluating this SK combinator results in over 100 million steps. Is there a way to actually see how many steps in Wolfram language it executed?
Oh, there's some functions for combinations, but I think they have some annoying overhead. But if you fixed point list, above list, right? Yeah, okay, let's try it. I think it's gonna be too slow.
Might blow up.
If I take this expression, oh, it's five times, right? If you want till the end, it's not reducing. How does it? The same, right?
Oh, isn't that the solution? That's the solution. The in is
No,
the
no, it's like this reduces to this.
yes, yeah.
Where it's 5 times then.
That was quick.
Or maybe clear all. Oh, hold on. Clear all. Okay. Now we're in business. Okay, so this, and if we do fixed point list instead, then technically length is the number of steps.
Okay.
But I think it's too slow to do it like this, to actually make this list, because there are too many expressions to store. Maybe they get very large. So if you just evaluate it using Wolfram language, is like immediate.
It's interesting. Yeah, we should maybe start with a smaller one just to test our understanding of this. Okay. And this will give you, this is counting the number of steps basically. The length of the fixed point list.
Well, you can try. I think it's like, I have a feeling like this has some annoying overhead. Let's just do a row replace list. Like this is like our 2 rows, right? Straight and like this. So a combinator. And just if I do replace all, right, and do the fixed point, I wonder how slow is that? Kind of slow.
Yeah, we should really start with that smaller.
I wonder how is this is so fast. Like what kind of optimization the main evaluation loop is doing, because it's not just applying rewriting rules to the expression. It's kind of tries to, yeah, because this is gonna like do the pattern matching every time, even though the expression is very large, right? But when you just evaluate it, you always know where you are in the evaluation, in the current tree. I don't know, but that's why it's fast. But when you do the pattern matching, it's space.
I believe it's using something that the developers refer to as technically in the literature, it's called magic, some kind of like wizardry. Let's try with the smaller SK expression. What was the one that we were testing previously that only had like about 50,000 steps?
Maybe I still have this. Maybe this one. Oh, that's not. That's fine. Written a weird way.
There it is. What's that? No, it's not that. Is that the right one?
Well, that's the right one. It's just it has to.
But isn't that the same as the one just the line below? Correct.
No, I don't think so.
There.
No.
No.
No, it's different. Like, there's two Ks. There's one K. Different. It's like this. No,
80.
some kind of 98.
Oh, that's very little.
Yeah, the board.
I thought this one.
Maybe.
I thought this one had like 20,000 steps or something. Is there a difference? What we had.
I was trying. Like this one.
Yeah, that looks right.
But this is like expression size, about 2,000 steps. But this is the steps
Actually traversed.
not the actual, just because you essentially relate all possible rules in parallel. But I think this counts just how many times each of those rules are.
There's some okay. So there's some parallel execution. Okay, so assuming everything, that's actually an interesting question. And is it parallelized in every location where it can be parallelized?
Yeah. So like if we do count 0, right, and every time this acts, do this count plus, and every time this acts.
Okay.
Actually, we even count them separately. CS, CK. I just to see what they. And let's just return this. Oh, see, it's not. No.
But that's still parallel, or what?
Why is it parallel?
No, I'm asking.
Maybe it depends on the actual evaluation order. Maybe this one is different from the whatever replaceable is doing.
Oh, I see.
I don't, because combinators, they are not optimal, right? It would depend, maybe. They would depend on what is the path.
Yeah, that's interesting. So, if we look at the click to copy code of how that was executed, does it show?
I think it just uses this function. Yeah, it's using this function.
Okay.
But it's in order to compute the size. Well, we just did that.
Yeah, but that's the old SK. That's the million one.
So essentially, that this one, but this.
Yeah.
Okay. Okay, extra bracket. Yeah, it's very slow for some reason. No, because there's too large expressions.
That's again a lot of memory. So the exercise here would be to see if we resolve, or if we evaluate this expression, this SK expression in Bend or just HVM1 as compiled C code, how much faster can it actually execute in a single thread?
Yeah.
Is there a way to execute Wolfram in one thread? Like, can you explicitly prevent it from running multi-core?
Oh, yeah. I'm pretty sure there is no parallelization happening when you do this.
Okay.
Especially even this, this is pretty fast. I'm pretty sure this is a single thread reduction of this combinator.
Okay, that's pretty impressive.
Right.
There we go, 1958.
Yeah. Yep. I don't know why it's like this is like a much faster.
And then, okay, so we've got 0.0005 seconds to evaluate that expression, which is multiple millions of steps. Could theoretically be less actual calculations depending on the parallelization. So what will be interesting is to see how if we could code that up in Bend, how much potentially faster it could actually execute.
Sure, yeah. Well, we've tried it, right? Like that was our original, well, with some modifications by Victor. We managed to make it essentially. This is like this example that we've tried right now, right?
Mm-hmm.
Just tried multiple times, like 100.
So if we do, and then the version that was in HVM1 compiled to C, how fast does that run?
Well, it was decent. Hold on. So this version, I was trying this with this code, right? So it's like almost instant. Need to implement some kind of looping.
Yeah, so what if we do okay, so let's do that million one. So this one's too quick. Maybe that longer SK expression will actually show up on our two decimal point timer here.
Yeah, we need to compile it in this form. Okay, let's think about it. So given this expression, right? Okay, first of all, there's like combinator.
Okay,
Do you
think could ChatGPT figure that out?
No, let's try it. Let's try ChatGPT. Good idea. No.
Just for the audience that are still participating here, the intention of what we're going to be doing here is to take an SK combinator expression and evaluate how fast it evaluates in Wolfram language versus a compiled HVM code version. Apparently HVM1 has certain optimizations that are not yet built into HVM2. So the idea here is we need to use HVM1 to leverage those optimizations. However, it also can only do one thread in HVM1. So you have a certain type of optimization, but you don't have the parallelization. So we're just going to see here how fast we can evaluate this thing on a single thread. So this is ignoring the parallel advantage of HVM, like the inherently parallelism of it. We're going to kind of like ignore that and just kind of like test the theory of optimal evaluation by putting this SK expression into an interaction net and letting it run. So let's
how to prompt
that's the
it.
intention, yeah.
And let's try it like this. The hell's happening?
Oh, is it calling Wolfram?
No, it's just formatted pretty. Tries to format it prettily. But it can call Wolfram, yes. If necessary.
Okay, back to drawing board.
No, if you have a good prompt.
So do it the other way around. So what you'll do is the following expression converts into this format. And then
expression.
And then put that there and then say converts into this format. Then take the top one and say, now convert this expression into the same format.
Actually, let's do it like in 2 steps. It's like, got it?
Yeah, cool.
Okay, good. Come on. Oh, look. Here it is.
So-
Oh, nice. Look at this. It's a function.
okay, that's useful.
Well, it's just like this dots is like not helpful. But
Okay, now
Yeah.
convert this expression into that format.
now do this one.
No, not do this one.
Nah, you get it. Look. Okay.
Beautiful. That's
Looks
cool.
fine.
Prompt engineering. Prompt engineering is a legitimate form of engineering.
Okay, so
It's like somebody who does HTML calling themselves a programmer. It's like, I'm a prompt engineer. I do software development.
How would this work? Oh, let's do
Some formatting.
hackery. Those almost. I think it's incorrect already. It shouldn't be like this. I would have wrote a function already.
Yeah, that's
just
always the risk of doing the LLM route, right? It's like,
Yeah.
you have to argue with the LLM or you argue with the compiler. where do you place your arguments? You fight with the machine or you fight with the AI?
Yeah. Oh, hold on. Let me just write one. So combinator evolve convert thing can be used initially. It's called almost like this list form. Not quite actually. Oh, application. Right. And it's full form. It's almost what we want.
You just do a replace on VS Code on that.
Application is up. And later is this. Okay. Later you just do traditional form. And you have this C dots, right? It should almost be because it's like this function. Fine. Put to string this traditional form that would make the brackets correct. And then you do the string replace of whatever this is.
Mm-hmm. It would have been more impressive if you just used regex.
I'm gonna use regex probably. Regular expression. This, how do you do it? This. One. Here. Two. And one. This is not matching. No, because it's no. Now we're gonna deal with the regex instead.
I shouldn't have mentioned regex.
I was pretty sure it's like dollar thing. I've done it for a while too.
I thought you had a converter for this stuff.
I do. I'm detecting this button. Or maybe that's dot. Almost. No.
You just coded manually at this point. See.
Okay, screw regex.
That was a test.
So that's detectable. Right. Just a usual bracket. Gonna like make this work.
Is regex Turing complete? I think it is.
Could be. What the hell now? What now? I'm doing something stupid. Maybe this. Ah. Marvels of live coding. Why is
So
it not?
ask ChatGPT what's wrong with your code.
Maybe this toString is weird. Oh, that is traditional. Put it down. That's why. Yeah, I just not used the string underneath is just. Yeah, it wasn't anything wrong with the regex. Just these brackets, they were completely garbled, I think.
Mm-hmm.
So what we do?
Okay.
Oh, there's like a space there. What?
So I mean, just for those who are trying to figure out what's going on here, we're trying to convert this SK expression into Bend language. An implementation into Bend. Almost.
What happened there?
Is there a comma between the XY?
I actually just want to do it like this. Why is it disappearing?
There's a comma missing, isn't it, between the second XY?
Where?
To the right. I'm just supposed to put a comma there. In between those two.
Well, that's the. But I don't want commas.
Okay.
Like I want it look like this.
Oh,
No commas. just up x, y. Or maybe that has to be shortest. That's better. I think it's workable.
Okay, let's see.
That was a waste. Okay. Look. It was fast.
Okay, so this is now, what is this, 100 million? Is this the 100 million SK Combinator tester? No, it's not.
Should do it this thing, this.
And an extra bracket there now.
No, there's a lot, but it was still fast. So it's pretty nice.
47,000. Interesting. That is interesting. Run that. Can you run that on HVM2? It's single thread, right?
Yeah. On HVM. This is a little bit slightly different form. Or this is the Reddit one, right? And I run it 1,000 times, right? If you do, and I think I already tried to compile it. And this is the compiler. So it's like 10 times less interactions, more than 10 times.
So we could take that time and divide it by 10. So what are we at? 0.002 seconds. More than 10.
Okay, this is for 1,000, right? I'll just do this. So where did it ever?
But is that all the interaction? Is that all 1,000 interactions on that iteration?
Yeah.
Yeah. Okay. So divided by 1,000. 7. Wait. That can't be right.
I'm not sure. Maybe that's not the one. Maybe that's not this loop. This is this program. I just run it directly. Even for one. So whether it's 1 or 1,000. Oh, it does differ.
Okay.
It was for 1.
Okay. So 700,000. Interesting. So what? So 727 divided by what was the other number there?
Divided by from HVM1. Yeah.
47,962. 15x. So if we take the time, what was the time that it gave us on HVM2?
Yeah.
Okay, that's divided by 15. My calculator's got an E in it now. So how many zeros is that? 1, 2, 3, 4. Interesting. 0. How do I? How do I? What number is this? Nick? The chat.
Like it's 0.0006.
3 zeros. Okay. Then when we did that in Wolfram language, we got 4 zeros.
Yes. I think so.
And do we
Or
know
just-
if that?
No, it was 3 zeros.
Oh,
No,
well,
it was
okay.
3 zeros.
Interesting. Do we know if this was single? Do we know if this is single threaded or not?
This one?
Mm.
Pretty sure. Single threaded. But this is also single threaded, right?
Yeah, that's the point. I want to make it. I want to give it an equal.
Actually, I don't know how to run this without. The C is parallel. I can't really compare it. You need to run the 1000 version.
If you run it in it's too quick. What if you run
But
it
you
in
also need
Rust?
to. Yeah, but you need to compare it. Compiled version, I guess. They still.
Wait, so are you saying that was it the compiled version that we checked?
See, like this is the difference between non-parallel and parallel.
Okay, let's understand that. So we're looking at 10x, almost 10x speed improvement, same number of iterations. Do you have 10? Do you have 10 cores?
It should be around 8. No, it should be 8 cores.
Okay. Yeah, that seems about right. Okay, and then if we compare this on HBM1,
Didn't pick too much there.
oh yes, Enrico. So it looks like you're running the C version, which is in parallel. The Rust version is single threaded. Yeah, for HBM2, right? Sorry. So let's. Can we loop the HBM1 implementation to get the time to be a bit longer than the 2 decimal places? But I think also there was something about trying to run loops in HBM1 that's a problem. If you try to just loop it over.
Really?
Yeah, I'm pretty sure Victor was saying that there's some kind of like not great implementation if you try to loop. So that's kind of the problem here. We're trying to do a speed check, but the problem is it runs faster than 2 decimal places of seconds. It's sort of the issue.
Right loop in HBM1. Something like this. See if it works. Like this? What?
Who knows how to write HBM1 here?
It's like a term.
Internal code.
Gonna
Maybe.
optimize it. So like it's just gonna run the argument, right? It has to be. Although how do we write it here?
Maybe if we just find a big enough SK expression, it'll bring us into the 2 decimal times. But we got it to show, didn't we? Or it was still compiling too quick. Where was the code that you ran in HVM1 that showed that large SK combinator cost and time? It's that one there. Yeah, it's still too quick there. And that's the largest SK combinator that terminates we're aware of, that we know of. Yeah, so we have an issue with trying to figure out how how long this thing takes. What if we just run this actual code like 100 times? Is that fair? Would that be fair? No, probably not, because you have
We
to.
can do. I think there's like a way to do time. Just is there a way to not just time it, but how do you use this repeatedly? You know, I think it should be able to do it.
It's quite a few bugs. Oh yeah, you could edit the compiled C code to show a more detailed elapsed time. Oh yeah, that's a good point. It's compiled C code, so we can just edit the C code directly. Yeah, let's just do that. Okay. Thanks, Enrico.
The HVM1 compiles to Rust.
Oh,
Right.
oh, no, but there's a way to compile to C, isn't it?
I know.
Should be. The memory allocation that HVM2 does on init might mess up the calculation. Yeah, yeah. If you just repeatedly run compiled C code.
No, it doesn't work. I know the compilation doesn't work at all. No, because you have this loop. It's just...
Yeah, yeah. On a two.
And this one. Right? Oh, here. Okay. Okay. Well, just included the whole pipeline. Good luck figuring it out. Where's the actual? Oh, that's too complicated. I don't want to deal with it.
Is this the? No, this is the actual computation stuff. Okay, but I mean, maybe that's a nice exercise for next time. We can figure this out.
Right.
Yeah. Okay. Let's maybe check in with the community, see if there's a way we can actually get a nice equivalent test here for this. Then yeah, we can report back with our findings. This is where it starts getting into the heavy troubleshooting, debugging session. But yeah, I think this is a nice stream. We're at 2.5 hours, so I think let's wrap it up here. We have an objective, and the objective that we can summarize currently is to say we have an SK combinator that apparently takes something in the order of 100 million steps to resolve. It does definitely resolve. We want to compare how fast this resolves in Wolfram, which is using conventional type of computation to resolve it, probably highly optimized, and then just see if we can get this interaction net version of computation to do it a lot faster, and then taking both sides of the claim of advantage into consideration, the inherent parallelism of it and the inherent optimal evaluation of it, and that's how we're going to compare things. But I think this was great. This was a nice comprehensive deep dive into various things. I got to talk about croissants, which is my favorite snack. So I finally figured out how to play steady-mate, and yeah, we've got a good understanding of the theory now. So yeah, I hope the audience enjoyed it, and yeah, we'll catch you guys on the next one. Cool. Okay, chat soon.